Hello from Chem Help ASAP. Let's see an example of J coupling in proton NMR with hydrogens being affected by different J values, including an example of geminal coupling. Here is a very simple molecule with a not so simple spectrum. Have no fear, we can quickly make sense of the signals in this proton NMR spectrum. Let's start with the downfield signal at close to 7 ppm and move to the upfield signals. Alright, here is the downfield peak. This is the CH next to the fluorine. It has two neighbors. One neighbor is trans with a larger J value. The other is cis and with a smaller J value. This signal is not a quartet. A true quartet should have a 1 to 3 to 3 to 1 intensity ratio. What is it? Okay, our signal from this hydrogen will be split by the trans neighbor HT with a larger J value, JT, into a doublet. Each peak in the doublet is in turn split by the cis neighbor, HC, with a smaller J value, JC. And here is JC, and JC is here as well. The resulting signal is now a pair of doublets, a doublet of doublets, or DD. All lines have the same intensity. In the spectrum, we can see that JC is the separation between these peaks. To calculate the J values, we read the position of these peaks in ppm, multiply by 400 million, because the spectrum is simulated at 400 megahertz, and divide by 1 million. JC is equal to 6.9 hertz. For JT, we can look at either that distance or that distance. Read the ppm values, do the math, and JT is 14.3 hertz. Let's now report this peak. The shift is 6.91. Multiplicity is DD for doublet of doublets. Integration is 1H. To give the J value, we'll write J equals 6.9, 14.3 hertz. Next hydrogen. Okay, this is actually another doublet of doublets. It's hard to be sure which hydrogen this is, but we'll figure it out very soon. It must be one of these two. To be a doublet of doublets, we need the hydrogen to have two neighbors. Each of these hydrogens has one vicinal neighbor and a geminal neighbor, the other hydrogen on this same carbon. Geminal hydrogens generally do not give J coupling interactions, but it sometimes happens, especially in alkenes. So this hydrogen, whichever it is, will have a J value for the CH on the right to give a doublet, and a smaller J value for the geminal coupling, JG, to give a doublet of doublets. What are the coupling constants? We'll measure them just like the previous slide showed. JG is either this distance or this distance. Go through the math, and JG is 2.3 hertz. For the other J value, we can measure that distance or that distance. If we go through the math, the J value is 14.3 hertz. 14.3 sounds familiar. That was J trans on the previous slide. So the proton we are looking at, this signal, must be trans to the other hydrogen. So we are looking at this hydrogen right here. Let's report it. The shift is 5.05. Multiplicity is DD. Integration is 1H. J equals 2.3 and 14.3 hertz. Really quick, let's do the last hydrogen. It's a doublet of doublets. It must be this hydrogen. We know its J values already. JC is 6.9 hertz. We know the geminal coupling J value. It is 2.3 hertz. How do we report it? The center of the signal is 4.93 ppm. Multiplicity is DD. Integration is 1 hydrogen. J equals 2.3 and 6.9 hertz. We have now seen a molecule with a multiplicity of doublets, which is pretty common. Please leave a like, subscribe, or ask any questions in the comments section. Thanks for watching. Take care.